In this video, we're going to continue section 2.2. So here I'll put in here, it's part 2 or continued, however you want to think of that. And we talked about patterns in the last video. This video, we're going to look at the problem solving aspect, and we're taking a little bit of a different spin than what we did from 1.1. We're going to look at inductive reasoning. Okay, so let me start by defining what inductive reasoning means. Inductive reasoning means you are using patterns, observations, examples, and experiments. So that's like the scientific approach. And experiments to form conclusions. Now, clearly, we have talked about patterns already in this section, so we'll discuss that when we're looking at inductive reasoning. But examples is also something we'll probably look at because we look at a lot of examples in mathematics. Okay, so to form conclusions. Let's go ahead and consider an example here. Or I should say, look at an example. Consider the following sums. So I'm going to write down 3 sums, and we're going to see what happens and try to make observations about it. Okay, so here we go. First sum is 4 plus 5 plus 6. And then the second sum is 2 plus 3 plus 4. And the third sum is 7 plus 8 plus 9. Okay, so let's look at these sums. We're going to add them together and see what we observe from this. Okay, so if I add 4 plus 5 plus 6, here, let's see, that's 9 plus 6 is 15. 2 plus 3 plus 4, that's 9. And then let's see, 7 plus 8 is 15, plus 9 is 24. Okay, so I want to look at these 3 results. And what I'm interested in is noticing if they have anything in common. So things that I'd be looking for when I'm looking for things in common is, are they all odd? Are they all even? Are they all divisible by a number? So looking at this, I notice the first 2 are odd, but the third one is even. I do notice though, and it might take you a second, all of these numbers are divisible by 3. Or you could say they're multiples of 3. But I can divide all 3 of those numbers by 3. And I wonder if that's a coincidence. Okay. So first thing I'm going to observe to see if this is in fact something. Okay. First thing I'm going to do is observe what happened. First of all, I'm adding 3 things every time. See that? Every time I'm adding 3 things. And I'm also noticing they are going in order, right? It's going 4, 5, 6, 2, 3, 4, 7, 8, 9. So we call that consecutive order, right? Each number is going in the pattern that we've seen from like the whole numbers or integers or something like that, or the natural numbers. We see that. It's a pattern where they're going in order 1, 2, 3. Okay, right in a row. So there's 3 of them. They look like they're going in order. And I just mentioned that we have these could possibly be all whole numbers. Let me just write that. They could be whole numbers. Oh, forgot the H. Whole numbers. Here, I'm going to use the number symbol because I want to save space. They could be natural numbers. Those are the counting numbers. Or possibly integers. So refresh our memory here. Whole numbers. Whole numbers are where they include 0. So the natural numbers or the counting numbers are just the numbers starting from 1 on, but whole numbers have 0, and then integers have the negatives and positives. Okay, so let's kind of throw in one and see. We're going to create an example. This will be part D, and we're going to create this. And let's see what happens if we throw in 0. Like, what would happen if we did 0 plus 1 plus 2? Okay, you're throwing the 0 in there. Let's see, that adds up to 3. And I'm like, oh, okay, that is divisible by 3. That works. Okay, well, let's try another one. let's try some negatives. Let's see if the integers work. So the whole numbers worked. This definitely seems to be working for natural numbers. Let's see if it works for integers. So I'm going to pick some negative numbers this time. Let's do -3, -2, -1. I'm throwing those parentheses just to emphasize that they're negatives. Okay. So -3 plus -2 is -5, because when you add 2 negative numbers, it becomes more negative. And then -5 plus -1 is -6. And guess what? That's divisible by 3. Okay, so now based on this, I'm thinking, I'm going to write down what I'm thinking. The sum of 3 consecutive, that means in a row, 3 consecutive integers, so it worked for the integers. Oh, here, let me put my little check mark next to the integers. Boom, it worked there. The sum of 3 consecutive integers is divisible by 3. This is my thought. So that's the inductive reasoning, me making this conclusion, okay? I'm concluding from these examples that this is probably true. It's actually possible to prove, and I'm going to show you that. It is possible to show that 3 consecutive integers are going to always be divisible by 3. We're going to use just a tiny bit of algebra to do this, so don't panic on me. It's not going to be a big deal, and I'm not going to require you to do this proof. I'm just going to show you that in math, we can come up with ways of knowing it is always true, and that's what makes math very powerful. Okay, so if I wanted to add 3 consecutive integers, the trick is the first integer I'll call x. That means that the second integer has to be one more, right? Because we're always adding 1 when we're looking at integers. So this is the first integer, and this is the second integer. I added 1 to get to the second integer. So to get to the third integer, I have to add 1 again, or it's going to look like plus 2, right? So if the number happened to be the number, let's do 11. Okay, the first number is 11. That means the second number is 12 and the third number is 13, which, by the way, if we add that up, grab your calculator, add up 11, 12, 13. That gives me 36, which I happen to know is divisible by 3. Cool. Okay, so these are how you write the numbers in general. And look what happens if we add them up. Again, this is going to use just a little bit of algebra. Sorry, let me go ahead and call this the third integer. We're going to add up the x's first. So how many x's do I have? I have 3 of them. And then I'm going to look at the numbers now. So if I add up the 1 and the 2, those add up to 3 also. Okay, and look at this. This, this right here is divisible by 3. How do I know? Well, there's a 3 out there. And so is this. This is divisible by 3 too. So both of these are divisible by 3. So if I'm doing this in general, this works every single time. If we're talking about consecutive integers, they're always going to be divisible by 3. That's kind of cool when you think about it. All right, let's look at another example where we're going to try to look at a pattern and see if we can extend it to be generalized. Okay, so if there are 15 people in a room, who will shake hands with everyone exactly once. Okay, so they're all going to shake hands once. How many handshakes are there? How many handshakes will happen? Question mark, and that's a W, a really weird looking W. Let me see if I can fix it. There, it's better. Okay, this actually is from the book. It's like the exercise at the end of the section, right before the homework. So we don't really want to figure it out what happens with 15 people. That's a long time to figure out. It would be easier to start with a smaller number of people, like 3 people. What happens when 3 people are in a room? How many handshakes happen then? Okay, so here, I'm going to draw 3 circles for 3 different people. Okay, so here, these are 3 people. How many handshakes are going to happen? Okay, so this person's going to handshake with this person, and then these 2 are going to handshake together for a total of 3 handshakes. And here, I'm going to abbreviate that HS. 3 handshakes. Okay, let's see what happens with 4 people. So 1, 2, 3, 4. Okay, so this person's going to handshake with this person, and this person. this guy and this guy need a handshake. And then also with that guy. And these two need a handshake. I don't know. I'm giving them weird labels. So let's see. Let's count up how many handshakes that is. So on the outside of the square, 1, 2, 3, 4, and then 1, 2. So 6 total. 6 handshakes. Cool. All right. 5 people. And in a second, I'll start looking to see if I notice any sort of patterns. Okay. 5 people. So here, I'm going to do the 4, and then I'm going to throw an extra 1 over here. All right. There we go. Yeah, let me give myself just a tiny bit more space, just so that drawing the lines doesn't become too cumbersome. All right. So I'm going to start with the top left corner person, and I'm going to make sure they handshake everybody. So they handshake this person, this person, this person, and this person. Okay. Now the next person, I'm going to go to the top right now. I'm going to make sure they handshake with everybody. Okay. So they're going to handshake with this person, and this person. Okay. Now I'm going to go to the guy here on the far side to the right. They're going to handshake with this person and this person. And then lastly, this person right here is going to just make sure these 2 handshake. And then the last person's done, right? Everybody's shook their hands, so we're all good. Sorry, I bumped my water bottle and scared my dog. Sorry about that. If you heard that loud noise in the background, that was me. Okay, let's count how many lines there are here. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 lines or 10 handshakes. Cool. Okay. Here, I'm just going to squeeze in one more on the side. 6 people. So we'll kind of do like this shape, which is called a hexagon. Kind of there. All right. Let's start with the top right person again, shaking everybody's hand. 1, 2, 3, 4, 5. All right, now we'll go to this person here. 6, 7, 8, 9. Okay. Now this person. 10, 11, 12. This one. 13, 14. And then the last person just needs to connect with this one. 15. All right. 15 handshakes. Oops. Didn't mean to put the extra dot in there. 15 handshakes. All right. Let's see if we notice a pattern. I feel like I have enough now to kind of go on. So to go from 3 to 6, I notice that it looks like we add 3. To go from 6 to 4, it looks like we add 4. To go from 10 to 15, it looks like we're adding. I'm sorry, I said 6 to 4 and I'm at 6 to 10. We're adding 4. To go from 10 to 15, it looks like we're adding 5. Okay, so it looks like every time I'm adding, I'm increasing it by 1. That seems like a reasonable pattern. I could double check with 7 people, but I'm going to go ahead and trust that I'm going along the right way here. So here's what I'm going to do. I'm going to write down what I had. So I had, for the first one, it was 3 handshakes, and then 6 handshakes, and then 10 handshakes, and then 15. Okay. And this is now for 3 people, 4 people, 5 people, 6 people. So I need to go out to 15 people. Okay. So 7 people is coming next. So this is for 3 people, 4 people, 5 people, 6 people. These are people. These are handshakes. Okay. Just table. Why not? Okay. Let me go ahead and draw that out then. If I'm going to make a table, might as well. 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay. So for 7, that means this time I'm going to be adding 6 this time. Here, I'm going to write underneath what we added. So 3, 4, 5. So now I'm going to add 6, which gives me 21. And if you're willing just to kind of work on your calculator with me, we'll go ahead and go through this without taking too long. I'm just kind of trying to make sure we see where the numbers are coming from. So now we're going to add 7 this time. So that's going to be 28. Now I'm going to add 8, which is 36. Then I'm going to add 9, which is 45. And I'm going to add 10, which is, oh, sorry. I just kind of realized I was getting a little bit off from the numbers above and I got distracted. Sorry. If I'm going to add 10, that's going to give me 55. There we go. Now I'm going to add 11. So here I added 8. Oops. I wanted to do it in blue. Sorry. 8, 9, 10, 11, which will be 66 under the 12. And then I'm going to add, oh, I'm just now connecting. I am just now putting together that each of these numbers in blue are the number that we are coming from. I just now put that together. Wow, that's so funny. All right, so now I'm adding 12. So this is going to help me kind of figure out where to stop. 12 to 66 is going to give me 78. And then I'm going to add 13, which will be 91. And then I'm going to add 14. Oops, I'll do that in blue. 14. And this should be the last one, which will be 105. And there we are, 105 handshakes. Now, granted, I could have fussed with trying to figure out what 15 circles and all the handshakes would have taken, but to have drawn 105 lines, I mean, that would have just been a really complicated picture. So yeah, it took me a little bit, but I feel very confident about my answer. And I noticed a lot of patterns. So very cool. Feeling pretty good about that. Okay. Now it's possible to have patterns not work out. Okay. Let me give you an example. This is one that the book uses. Let's say we're going to look at regions created. Oops, regions created on a circle by connecting. Sorry, that's an N. By connecting points. Okay, what I mean is this. Let me draw it. So we have a circle, and let's say we have 2 points on the edge of the circle. So connecting points on the circle. 2 points. Okay, so let's draw a line across, and let's see, how many regions have we created? Looks like we have 2 separate regions here. Here, rather than write regions every time, it's just going to take forever. Let me label that these are going to be the number of regions here. Regions. Okay, 2 regions. Great. Let's look at if we have 3 points. 1, 2, 3. Okay. So, and this is kind of building just like we did off the handshake, that we're going to be connecting all of these and just seeing how many regions we've connected or created. Okay, so it looks like 1, 2, 3, 4 regions this time. Okay, so let's increase to 4 points. And they could be in like, they don't have to be perfectly symmetrical. Like it'll still work regardless of how we set it up. 4 points. Let's see. Let's go here, 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 and then here, and here, and then those 2. Okay, so let's see how many regions. I have one tiny little region right here. 1, 2, 3, 4. So there's the outer regions. And then I have 1, 2, 3, 4 inner regions for a total of 8 regions. Okay. I'm going to keep going, but I wanted to pause here just to kind of see if we see a pattern. And what I'm kind of noticing is that from here to here, right, it's kind of looking like they added 2 or possibly multiplied by 2. And now from here to here, it's looking like, okay, it looks like they're multiplying by 2, right? Because 2 times 4 is 8. So I'm wondering if it's kind of geometric. All right, let's try 5. Oops. Let's see if that works. Oh, okay. I'm sorry. Got mad at me. 1, 2, 3, 4, 5. All right, I'll do my best here. So one line, and then I'm going to go from the top left. 2, 3, 4. Okay. And now this guy to this guy, to this guy, to this guy. All right. And now this to here, and then this. All right. Wow. All right. Let's count these regions. This might take a second to kind of do it. I'm going to do the outer ones first because they're kind of hard to see. So it looks like we have one region here. 1, 2, 3, 4, 5 outer regions. Okay. And then we have 6, 7, 8, 9, 10 of those. And now I'm going to kind of look at the star inside. So 10, 11, 12, 13, 14, this little one, 15. And then the very center, 16. All right. So it's looking like maybe times 2. Let's try one more to be sure. 6 regions. 1, 2, 3, 4, 5, 6. I'm sorry, 6 points, not regions. Okay, here we go. Connecting. So I'm going to start with the top left. Here we go. 1, 2, 3, 4, 5. Okay, now this guy. 1, 2, 3, 4. Okay, this one. 1, 2, 3. This one. 1, 2, and then these 2. 1, 2. Okay. This is going to be much harder to count off, all right? So I'm going to do my best. We're going to start with the outer regions. So this little region right here, which is kind of hard to see. 1, 2, 3, 4, 5, 6 little outer regions, the best of my ability. 6. Okay. Now I'm going to go to the next one. 7, 8, 9, 10, 11, 12. And now I'm going to go to the inside here. 13, 14, 16, 17, 18, 19. There's a tiny one right here. 20, 21, 22, 23, 24. Okay. Now the inside. 25, 26, 27, 28, 29, 30. Huh. I'm looking like I got 30. I want to say it's supposed to come out to 31. I'm going to double check that one more time. All right, but I'm going to count it all at once. So let's see if I can do that. And here I'm going to zoom in a little bit just because the regions are kind of small and hard to see. Okay, so starting at the top. 1, 2, 3, 4, 5, 6. 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29. And now I'm like, got less that time. Okay, tell you what. I'll go with my original of 31, which I really feel like I counted 30. Okay, so I paused the video, and as you can see, I like counted each region and I got 30. I did get 30. So that's not times 2. It isn't. If you times 16 by 2, you don't get 30, you get 32. So yeah, it didn't work. And it wasn't supposed to, but I felt like the first time I had counted, I got 31. So it's fine. We got 30. It doesn't work all the time. We can't always just assume the pattern is going to continue. There are instances where it doesn't. Now, for children, which is what we're gearing towards, right? Kids, what we want to do is we want to make sure they understand it doesn't always work. And then maybe discuss this concept called a counter example. So here, I kind of zoomed out a little too much when I finished counting it up. Sorry, there we go. All right, let me come down here and let me define a counter example. And as it kind of sounds, it sounds pretty obvious. A counter example can show a counter example can show a statement is false using one instance where it doesn't work. So in math, in order to show something doesn't work, you just need one example that fails, okay? One counterexample can do it. That's all you need. So let me give you an example of where we might use something like this. Let's say we want to say whether something is true or false. This is a great place to use counterexamples. Okay, we'll do two examples here. So let's say the sum of any four numbers is divisible by 2. Okay, so let's check this out and see if we can possibly find a counterexample. So what we're saying is that if we add 4 numbers up, it's going to come out to an even number. That's how you know it's divisible by 2. Okay, so let's start with the most basic. Let's do 1 plus 2 plus 3 plus 4, which I think is going to end up being divisible by 2. But that's all right. We're going to start somewhere. Okay, so 1 plus 2 plus 3 plus 4. Let's see, that adds up to 6, 4, 10. Okay, so it works there. Let's try 2, 3, 4, and 5. Okay, let's see what happens here. So let's see, that's going to be 5 and 5. That's 15. All right. Let's try another example here. Let's do, oh, I just realized, I just realized they didn't say consecutive. Do you see that? I like automatically from our problem earlier went to using consecutive numbers, but that's not what it says. It says any 4 numbers. Okay, let's try something different. Let's do 2, 3, and 4, mainly because that adds up to 9. All right, and I can see that adds up to 9. So in order to make sure it doesn't add up to an even number, if I added 6 instead of 5, that'll give me 15. Aha, that's a problem. So in this case, it didn't work because I used consecutive and I didn't need to. It was false. Any 4 numbers supposed to be divisible by 2? Not true. Okay, not true. Let's try another one. Let's say the sum of any 2 even numbers is divisible by 2. Okay, so an even number is already divisible by 2. Like, for example, 2 and 4. So if I add 2 and 4 together, that does give me 6, which is also divisible by 2. Okay, let me pick more exciting even numbers. Let's do 22 and 36. Let's see. Adding that together is going to give me 58. Okay, so I kind of feel like it makes sense that if the numbers are even, they're probably going to add up to be something that's even. Now, I'm going to show you it's possible to prove it. Let's do another little proof here. And let's not get crazy. Let's not get scared about the proof, okay? I'm going to kind of rationalize our way through it. Like, let's consider the number 6. If I have the number 6, it's divisible by 2 because it's even, which means 6 divided by 2 is 3. Or in other words, we could say that 2 times 3, oops, sorry, use the time symbol. 2 times 3 is 6. Great. Okay. Also, another number that is divisible by 2 is 16, right? Because when I divide it, I get 8. Or another way of saying that is 2 times 8 is 16. Cool. That's an 8. Let me make that look more like an 8. Okay. So the idea is even numbers always can be written as 2 times something because they're divisible by 2. So if I want to take 2 random even numbers, let's say 2 times here, I'll use x since that's what I used earlier. 2 times x is an even number. And so here's an even number. Even. Wow. I did not want to write very nicely. There we go. Even number. And then another even number. Here, we'll call that first even number. And then the second even number could be 2y. And if I add those two together, guess what? this thing is divisible by 2 because I could divide 2 into both of these, right? So divisible by 2. So yeah, it works. This statement is true. And it makes sense that it's true. I really didn't have to go through a proof. We could probably just reason our way and say that if we're adding two numbers that are divisible by 2, that result is always going to end up being divisible by 2 as well. And there you go. That is inductive reasoning.